I didn't realize that it was 2 minutes past. You can get a sound reflection off the other computer. Okay, I didn't realize it was 2 minutes past. You can get a sound reflection off the other computer. All right. So somewhere in all these videos, I've done a derivation of that equation. So instead of harboring on that, I'm going to look at the terms that are in the equation. Hang on. Drop the pen on the ground, but it didn't damage anything. So let's look back at it. So the important things that come out of this, and you can read through the derivation itself. What he's doing is he wants to find the resultant force. There's two things that you always want to do. Find the force and where it's located. Okay, so the force is pretty easy. It's basically that. And if the gate's tilted down a funny angle, you can change that height out to this. And then what you find out is if you've got an odd shape, in other words, sorry, this shape is what a person that sat right here looking that way at this gate, this is what he sees. So you see something like this, and they're going to integrate over the whole area to find out the little d force over this. And of course what you do is you move the thing, you create this dx and dy, but sorry, one of the things about this is this strip. If you integrate this way, this strip would look like this, and it would be at the same depth. So what you can do is integrate across this thing. Well, the end story is you carry through the integrations and you get this equation. What is this? This is the value of the resultant load, the gamma of the fluid, the height down to the centroid of that area. Okay, so let's take a look at that. So you know what the area is. I mean, say you knew that area. I mean, it's an odd looking shape, but we can make it normal. We can make it 10 by 20. So you know now the area is 20 by 10 or 200. Now the centroid of that would be straight right there. But let's go back to his shape and say, okay, he has defined this oddball shape. He has identified the centroid of that shape. And there's a specific point there. So he finds the resultant force is equal to gamma. Okay, some will call it that, where that's the centroid. He's calling it that. More often than not, I've seen it this way. And so it is the depth from the top of the water, and I use water exclusively as a term here, but it doesn't have to be water, it can be oil, anything. But down to that location. And so now, is that where it's at? No, that is not the location of the load. He's showing you that right here, so that you use the centroid to find the value of the load. not the location. How do you find the location? Well, you do the same thing you do in statics. What you do is you find your, here, why am I trying to draw this? He's already got it drawn here. What you do is you go out, you say, well, if this is my df is equal to gamma a d area, which is, I'm just pulling this out because you integrate that in a second. But here's the thing. If I want to know the x location, he's calling it the y. I'll call it y resultant. Then I'd have to put a y here. And then I can integrate. What you end up, that's going to find the resultant moment. And then you work your way through it, and you can find the distance, how far below the centroid is the location of the resulting force, or the center of pressure is what he calls it. So when he goes through that derivation, what does he do? He takes the df that you had before, slips a y in there. So you had, well, there's your still gamma, but you've got that squared. And now this squared should be something familiar to you. It should be that, the second moment of the area. Now, before you go on any further, you realize that what you've done is you've taken the FR, slipped it under here. Okay, this last step is the part that sometimes gets people. Okay, F resultant is equal to gamma H bar A, right? But H bar, oh, he's listed them together, is this component. So he's now taken this FR, sticks under there. So what he's doing is he's doing this. He's doing y sub r. I'm going to basically do the intermediate step. Y sub r is equal to all this mess, integral of gamma sine theta y squared dA over, and you take this and put under there gamma a yc sine theta. Now what you find out is these don't vary. It can be pulled out, and when they do get pulled out, they offset these. So you, on the bottom, you get that. On the top, you get y squared. And your final equation ends up being this. Now, what is this? Okay, so I look at it, I'll generally reference something called a delta, which is this term. And that is I. Okay, this is again a little weird compared to statics, and that is the second moment of the area about the centroid. That is the location of the centroid, and that. Now, what is this on the drawing? On the drawing, it's this. It's the distance below the centroid. Okay. Now we're going to do a simple problem in a minute, and we're going to do it as a matter of fact, let's just do it now. Here. Nope. Here. I wanted to create that. Here. I'll just do it this way. Can I do... Hang on. Come on, go away. Wonder what? Let's say copy, paste, paste, paste. Just paste a bunch of pages so I can start off. Okay, so let's take a case in point. Let's say we have a gate or a section of a gate, and we're just looking at it. The person over here stood here, and this is the key. He sees in his mind this. Okay, here, let me drag it backwards. Dude's way back here. This is what he sees. He sees a gate that's, let's just make up real numbers here. 15 foot in this direction. 10 foot into the board, or into this paper right here, or whatever this is. It's not a board, it's not a paper, it's electronic media or whatever. Now let's put the water height up here at 5 feet. Now, let me do it this way. I'm going to move this all the way over here, and you'll see why in a minute. It's 5 feet. So, to complete it and make it kind of a problem, we'll say this is a big section of concrete. We'll say there's a section of concrete here holding the gate back. But what we're interested right now is just the force on this gate. There's your centroid, and somehow there is a resultant force at a certain location. Let's reference it from this point here. Now, let's compare back to the drawing, because it's important to keep up with the way he's developed this. And by the way, it's not just here. They've developed this same equation everywhere. So, I was trying to select everything and delete it all at once. Okay. First, he has defined this location as being something special. It's the origin. It is where a line that comes directly from the gate crosses the free surface of the water. In the case I just drew, they don't have that. It doesn't matter. This is somewhat of an imaginary thing. Now, the other thing I didn't do is I didn't talk about the angle of this gate. So let's go ahead and do that. Now, how does it relate back here? Because he has an angle right here. And so let's just use an angle of 30 degrees. Just because at least one of the components out of that will be okay. So, what does this mean? Let's compare back. He's drawn a line 90 degrees to here. Here. 90 degrees from here. And then he starts measuring from that towards points down onto the object, like the center pressure or something like that. So, in your mind, what you do is you take, then you're looking down that direction. Well, first thing, you got to find this point. Well, how do you do that? Well, first of all, if I look at it, I see a triangle, which is here, here, and here. And let's see if I can do this. I don't know if this is possible to select an object like that and then move it. Yes, I can. And now what I see, and that's the reason I put that little top on it, so I'd have something to grab. So you got a 30. This distance right here is a 5. Can you determine that distance? Well, to me it looks like the sine of 30 is going to be equal to the 5 over the question mark. The question mark is going to be 5 underneath. This sounds really weird. Sine of 30 underneath it. So what we're eventually going to try to do here is work this problem two ways. One that's a traditional way and one that's using this set of equations. And if I can get through that in one class period, that will probably be enough to take us into the next class period. Let's pop off that word of the day because I'm back here in this area. I don't know what that was. Content. Let's see, my email. Monkey. Okay. Now where was I? Okay, let's head back to this. So, in this triangle, oh yeah, I was going to head over to get the calculator up here. And I was going to do 5 divided by sin with a degree of 30. 10. Should have known that. So this value is 10. So the distance from here to the edge is 10 foot. The distance from here to here, 5 foot. Now, in his equation, we have two equations. F is equal to gamma, and I like to use H bar and A. And then I like to use the delta is equal to I bar X over Y bar area. Those are the only two equations you need. So, let's see what we can do. Okay, so I know that the centroid of this thing is 7.5 down this thing. So now I'm looking at a triangle that is like so. Okay, there's my selection point. Actually, I didn't even need to do that, did I? But I did it. So now I've got this triangle, and it says it's 7.5. And what I'm interested in is the extra distance down here. So I'm interested in this. But if you stare at this and compare it up to here, this is still 30. So by making this analogy, this is 10 and this is 5. That would be, this is 7.5 divided by 2. So I don't know what that is total, but that's okay. So let's just 3.75. So that extra distance here is 3.75. That means the distance from the top down to this location of the centroid is this plus that, or 8.75. Okay, so looking for the force. Let's call it water. 62.4 pounds per cubic foot. H bar, the distance from the top of the water straight down till you touch the center or the centroid of that gate. 8.75 times the area, which was 10 by 15. Now I can get 62.4 times 8.75 times 150 is it. That's all there is. 81.9. Okay. 81900 pounds. Now here's the thing. There's in this section, there's a lot of forces that are fairly large. Think about a 15-foot a 10-foot real gate that's sitting 5 foot underwater and has nothing but atmospheric pressure behind it, that's a lot of force. That water is pushing really hard on that gate. Now I need to know, where is the load located? In other words, this is actually where the force is pushing at. And in my little world, oh gosh, I think I got that off, didn't I? So here's, in my world, well, first of all, I hate that, but this is the distance down below the centroid at which the resultant force is. It'll make sense when we work this the second way. So what is bar? And you know, in statics, I like to do XX. And for this, it's 1/12 base times height to the third. So what you do is you take the orientation of this dude, where this is the base and this is his height. So 1/12, the base being 10, the height being 15 to the third. You know what? Before I calculate this, I'm going to go ahead and deal with the rest of this, because what I really need is I need the total delta. So I'm just going to put 1/12, 10, 15 to the third, that's this, over the area, which is 150. And what is y bar? Okay, let's take a look at this. This is an interesting thing. Okay, again, I'm going to make use of this, being able to draw a thing out of here. So you go down here to the centroid, you come up to here, you come over to here. Now, if you grab this, what you find out, I have no idea what that is. Move it to the side. What you find out is that this distance right here, take a close look. I'm going to put it back on there and I'm going to pull it back off. Put it back on there and then take it back off. And now I'm going to say this is H bar, this is Y bar. And it's true, that's 30 degrees. So we already found this being 8.75, right? Let's see what that might end up. Now there's an issue I've got right here. Hang on. I'm trying to make sure I got my everything. Well, let's go ahead and do this. Something's bothering me right here. And the reason it's bothering me is because I can see a 7 and I can see a 10. And that puts me at 17.5 from this point down to the location of the centroid. But, and this is supposed to be 30 degrees, is that obeying this correctly? So, there's a sine of 30, which is supposed to be a half. 1/2. Is that equal to 8.75 over 17.5? 8.75 over 17.5. Oh, it is. Okay. Okay, I was hung up for no good reason. So in fact, let me see if I can review this. So we found the H bar right here. We looked across at this Y bar here. I thought I had something wrong with the geometry because I kept looking at these two numbers saying that doesn't divide out to be 1/2 when in fact it does. And I guess what I was seeing is in my mind I saw a 6 there, but there wasn't a 6. So sorry about that delay. So that means now that this in fact is equal to Y bar. Now, let's say this is 10, 15 to the third over 12 over 17.5, 150. Let's figure all this up. We're probably not going to find that it's that much. Okay, 10 times 15 to the third power divided by 12 divided by 17.5 divided by 150, and it ends up being 1.0714. Usually this is a reasonably small number as compared to the length that it goes down there. So now what does that tell you? Okay, it tells you I've got such a mess up here, but it tells you that the location of this load is 1.07 below the centroid, and it's that amount. How is that helpful for you? Well, if you redid this and you made it so that you were wanting to know the force that was being held by this little concrete piece right here, and you said that's a hinge, then the hinge force would be here, but you could sum the moments about it. So let's try that. Here's what I'm going to try. I think, yeah, I can select. I don't know what I'm going to end up with, but whatever I get, I can do a copy, and then if I just do a paste and drag it down here. Now hit the escape key, and I don't need this, and I probably don't need those middle marks. They may be attached together. Yeah, that item might be attached to the other. Yep. So for some reason, those two marks are attached to that. Okay, so what you do is you sum the moment about the hinge. I don't like this pen, it's too big. You sum the moments about the hinge, and you get, okay, this, remember this was 7.5 down to the centroid, and then underneath it was the 1.0714 equals to the force resultant. Now let's go ahead and make this be positive. So that means this. Now, okay, let me move this over. It's fluid static, so it's got to be 0. Since I'm taking the moment about this hinge, the hinge force in the Y and the hinge force in the X don't matter. By some of the moments, I'm only looking for this force and the resultant force. So I'm back here with the 0. FR times the distance, which is way out here. 7.5 plus 1.07 And the minus would be the resultant force times the entire 15 foot it's on the other side. Gives you the resultant force held by this thing. Okay, now I figured out my resultant force a minute ago. 81,900 divided by, well, first times 8.5714 divided by 15. 8190. Oh, and another O. Times 8.5714. And I'm sure there are extra digits, but I don't have them. 46,800. So I'm going to say 46,800 pounds. Now, let's approach this a different way. Okay, let's keep our mind. This was the resultant. Okay, so here I'm going to highlight things that we're going to look back at. This, and this, we're going to look back at. But this time, what I'm going to do is I'm going to take my mess of a drawing and I'm going to try to get rid of some of this stuff. And you know what? I'll get rid of it after I make a copy of it and start reworking it a completely different way. Copy, paste. I'll drag it down here. Keep dragging it to the point where I can start with a fresh thing here. Yeah, you know what? I'll just draw a line here between it. This is the other way. Okay, now what I'm going to do is I'm going to copy it again over to the side with some things moved off of it. Now, let me get, gosh, I don't know why I made that a dotted line. I wasn't very good about handling some of it. Okay. So 7.5 down to the centroid. 7.5 down to the centroid. Another 7.5 over here. So we already found that this was 3. What? I don't know what's going on there. 3.75. In other words, this distance from here to here was 3.75. I contend the next distance, since that's the distance to the centroid, that's a 3.75. So if you're looking to the distance to the far edge of this plate, it will be 5 plus 2 times 3.75. Or, now here, 2 times 3.75. 7.5. Okay, so let's do this. This will be 7.5. Now, let's look at this real close. Okay, I'm going to show you a different way of coming up with the same thing. And I'm going to get rid of that too. Okay. So you got 5 down to here. Now, I have a triangle that looks like so, and so. If I took that triangle, and let's do that, and drag it off here, first of all, when I bring it off, the distance from here to here is the 15 back here. Let's drag it over. So it's 15. It's still 30 degrees, So this is 15 divided by 2, or 15 times the sine of 30, but we've already figured out that's a half. And what is a half? That means that the distance from here down to this point is 7.5. Well, if 5 and 7.5, that gives you the distance to the bottom of the plate, distance to the top of the plate. Why is that important? Well, because now what we're going to do is something really interesting. Now that we've got that, I'm going to do a copy again. Or should I just do it on this drawing? Yeah, I'll just do it on this drawing. So if we were to draw the profile, the pressure profile, you know what I'll do? I'll do something like change the pen type. Somehow you could change the pen type. No, that's, I don't know. Here, I'll use a weird color. So the pressure, well, that's too big. Here. There's a pressure at this point which is equal to gamma times 5, because it's 5 foot from here down to that location. It turns out as you go deeper and deeper into the water or into the fluid, you find out the pressure increases. Why were you interested in this over here, which ends up being 12.5, is because the pressure is larger here. Now, what you can do is say, stare at that for a minute. Pressure acts as a distributed load that's linearly varying, always linearly varying. The deeper you go, because remember, the pressure is equal to gamma H. As you move deeper, pressure increases. Gamma stays the same. So going down deeper and deeper underwater, you get a higher pressure. Now, to me, this looks exactly like a statics problem. Let's see if I can grab the statics information here. But before I do, I'm going to basically, no, I don't need to get that quite yet. I'll need to recognize that the pressure over here is gamma times 12.5 on the right. So we'll go ahead and keep that. So what I'm going to do is I'm going to try my best to pull this off in a way that I can make a free body diagram out of it. Uh-oh, I don't know what I'm going to get. Uh-oh. Here, I can fix this by doing this. Okay. Copy. Hey. It looks like something happened there, but it's okay. I can copy this. And now I have a problem that's just a statics problem. Tilt your head 30 degrees, and I have nothing more than a statics problem. On the left, we're going to take this as water. So on the right, 62.4. Let's go ahead and change back to 62.4 times 5 gives me 312 pounds per square foot. So now I've got that on the left. Now I do have a total of 12.5, but this, you could think of it like this. You have two pressures over here. One linearly varying and one that's uniform. So here's your uniform one. There's your linearly varying one. So what is this? This is 5 times gamma. Well, the total has to be 12.5 times gamma. So guess what? So the extra depth, so remember, I know the drawing is kind of weird. Remember, oops. Remember, this was 5 foot. Okay. And then we determined from that elevation, this was 7.5. There's a lot to remember. Once you work one of these problems, it makes sense. So now I'm going to convert this. Okay, let me find these values because that's still 312. This time it's 7.5. 5 times 62.4. 468. Now I'm going to do something interesting and say, hey, wait a minute. Okay, right in my copy. There we go. So now I'm going to take this problem and do like you do in statics and just say, hey, I want to convert it to 2 loads here. One, it sits right at the centroid that comes from the uniform load, and then one that's the triangular load, and it's 1/3 from the bottom. You have to remember this is 15, so conveniently it's divisible by 3 into 5 individual chunks there, or 5 length chunks, or whatever. Anyway, so what is this? You have to remember this is 312 pounds per square foot. A uniform load put on this object is a force total due to the uniform load of 312 times 150, or 312 times 150 becomes 46. Is it 800? Yeah, 800. Now, we want to know this load. Now, to do that, we got to have that area. Okay. Now, let me rephrase this a little bit. Let me hit the Control Z. Yeah. So this is a uniform load that is applied over the whole thing. The triangle isn't a uniform load. It's essentially you have to take half of what it would be as a uniform load. I think I'm making sense. I hope I am. So what I'm going to do is take it as a uniform load. Okay, and then really, since this part that's missing is the same as the parts that's there, I would divide it by 2. I hope that makes sense. So it's 468, that's the value, times the same area, because it's over the same area, but half of it is missing. Okay, give me a second. 468 times 150, and half of it's missing, 35,100. Now, hey, wait a minute. Did I forget some digits? Oh, what am I doing here? Wait, Control. Okay. 46,800. Oh. Okay. So let's say we got 2 loads here. So let's figure out the total load. 46,800 and 3510. This is from the triangle, and this is from the uniform. Okay, let's see. 3510, or it's not really that, but 46,800 becomes 81,900. Did I copy that down right? 81,900. Now, you look back here, 81,900. same number. The difference is now on this one, I've got a load here and a load here. Before I had one load. So essentially the other way, you're taking these two loads, you're making them into one load. You don't have to do that if you do this individually like this. And so now you can sum the moments about the hinge again. This time you get two loads. You get, okay, I'll do this one first. 46,800. The distance down to it is 7.5. And I also get the 35,100. And the distance to it, okay, now this is the thing. This is a triangle here. And if this is 15, I can break it into three sections of 5 by 5 and 5. So it turns out the distance from here down to this second load is 10. And you still got, and you still have the resultant times 15. So let's see what our resultant ends up with. 46,800, 7.5 plus 35, 10, or I'm sorry, 100 times 10 divided by 15. I should be able to get that out before we're done here. 100 times 7.5 plus 35, 100 times 10. Now I've got a problem here. I don't have the initial bracket. Divided by 15. 46,800. Okay. So we already checked that out. That was that. Is the 46,800 the resultant load? 46,800. So what you find out, hang on, it's not behaving. What you find out is both ways come up with the same answer. There's a restriction on this method that I guess I'll talk about next time, because I think we should go ahead and go. So thank you. I am sorry that I was sick. I was sorry for myself that I was sick yesterday. I did not want to do this. And I think I might be able to make it in on Wednesday.